Right. So our second talk of the day and our second available I guess I should say reading group option. We have Caglar here from the University of Wisconsin-Madison, who's going to give us a talk about link functions on currents, and I'm excited to see what you have to say. So thank you for coming.
Yeah, thank you for the invitation to speak. It's a great pleasure. It was great to listen to Julia first too. I can't top that, but I'll try to do as best as I can. So I'm going to talk about geodesic currents a little bit and talk about this survey paper I wrote with Vivek Erlandson. It's mostly a survey paper, and it has two things. One of them is about counting curves on surfaces, and the other one is I'm hearing myself, which is bad. How can I make that go away?
If you mute yourself on one of your devices,
Let's see.
or
Just a second.
maybe in the Zoom window, you can stop the audio connection.
Disconnect.
Disconnect. Yeah.
Okay. Hello, hello, hello. Okay,
Yeah.
I'm not hearing myself. Okay, good. Okay. Well, you can see my cat. Can you see my paper now? Okay, you can see my paper. All right. What was I saying? Okay, there are two aims to this survey paper. One of them was trying to recast Mirzakhani's curve counting result using geodesic currents. This is the work done by my co-author Viveka and Juan Soto, Kazra Rafi, and many other people. And the other one is about dynamics of surface homeomorphisms. Surface homeomorphisms acting on curves. And naturally, since we're talking about curves, these are going to live inside the space of geodesic currents. I'll tell you in a minute what that is. But sort of my motivation for doing dynamics comes from geometric group theory. So I'm a geometric group theorist. I think about groups, infinite groups, and I think about infinite groups of low-dimensional geometries and topologies and their symmetry groups. So I think of dynamics as a tool that I picked up along the way. I didn't really become a dynamicist, but I sort of picked up these tools that helps me understand the structure of groups, subgroup structure of groups, or the geometry of objects. So maybe the motivating thing for the second part of the paper comes from an old theorem of Tits. This is more than 50 years old. It's known as the Tits alternative. So this is originally a theorem for linear groups, which says that any finitely generated linear group, any finitely generated linear group has one of the two. It's either virtually solvable, okay, solvable is sort of hard to remember, but you should just think of them, it's like abelian-like, or it's constructed from abelian pieces, or it's very large in the sense that it contains a free group of rank 2. Okay, so this is the classical Tits alternative proved by Tits for general linear groups. So if it contains a free group of rank 2, it actually contains free group of any rank. So it just means that if you have a group, it's either like built up from really sort of easy to understand, undergrad, easy to understand pieces, or it has free groups, so it's incredibly rich. Turns out a key thing in proving this Tits alternative is what's called the ping pong lemma. Which says the following. So I'm gonna doodle some pictures. So I'm gonna have some sort of a topological space X, and I will have a group G acting on this topological space X. So this showed up a lot in Giulio's talk, and in a lot of the places in their paper, they also use a version of ping pong lemma to get free subgroups, etc. So what does the ping pong lemma says? It says if for any elements, for infinite order elements A and B in G, if you have subsets, let's say XA and XB that are disjoint, if there exist disjoint subsets XA and XB inside of X, so that every power of A maps everything in XB to XA. So A to the K of XB is always mapped to XA for all K, which is non-zero integer. And every power of B maps XA into XB for all K. Okay. Then the group generated by these two elements is a free group of rank 2. So then the group generated by AB is isomorphic to a free group of rank 2. So it means the following. So if you Julia was talking about a non-elementary condition, it means the following. If you have two interesting elements in your group, interesting means that they are sufficiently disjoint from each other, then you can use these elements to get, in some sense, very many interesting elements. Okay, so that's the ping pong lemma. So this Tits alternative was originally proved by linear groups, but then it was proved for many other things. One of them was non-elementary hyperbolic groups, meaning that any hyperbolic group which is not virtually cyclic also satisfies the Tits alternative. The mapping class groups, so this is something I'm going to get into in a minute. This was done by Ivano and McCarty independently. And automorphisms of free groups. This is done by Bistvina, Payne, and Handel. Okay, so I want to talk about this mapping class group case in particular, but how does Ivano, or how does anyone actually prove the Tits alternative? They go through this ping pong lemma, and then how does actually anyone prove ping pong lemma? They understand dynamics of individual elements. So this is my introduction to dynamics, of individual elements. So one thing that you probably know if you're familiar with hyperbolic groups is that in a hyperbolic group, an infinite order element acts with north-south dynamics in the compactification of the Cayley graph. So some north-south dynamics. So this is a notion that that you can talk about in any setting. But let's say that you have a group acting on some compact metric space. And G is an infinite order element inside of this group. And we say that G has north-south dynamics if the following picture happens. Well, it really looks like north-south dynamics. There is a north pole and there's a south pole in your space X. these are fixed by the action of G. So Gn is always n, and Gs is always s. And every other point is attracted to the North Pole under forward iteration. So if you have a point like this, and if you apply powers of G, it is going to be attracted towards n. Okay? So G to the n of x converges to n, and G to the negative n of x converges to s for any point which is not x and n. Okay? So this is called north-south dynamics. So you can imagine if you have north-south dynamics, you can create a ping pong set like this. So you can use neighborhoods of the north and south pole to create ping pong sets. So the north-south dynamics business is then useful. So having north-south dynamics will give you a ping pong table. And that will give you eventually Titz alternative for your group, or maybe other subgroup alternative theorems. Okay, so I want to talk about the specific case of the mapping class groups. So the mapping class group, let me denote it by MCG, but usually I denote it by mod S. Is the group of orientation preserving homeomorphisms. So this is orientation preserving homeomorphisms of a surface up to isotopy. Okay. So you probably have seen some examples of these. Maybe you have some sort of a closed surface like this. One example of an orientation preserving homeomorphism is a Dane twist along a simple closed curve. So what you can do is you can cut your surface open at this curve and then twist one side by 2 pi degrees and then glue it back. So that's one type of a homeomorphism. So when you apply that map, the alpha, this curve goes to this curve that winds around that curve and continues like that. Okay, so that's one type of a homeomorphism. And you can try to do this at many different places. There are also kind of boring types where you get the homeomorphism from the symmetries of your surface. Maybe you draw your surface perfectly symmetric like this, and you click by 2 pi over 4 degrees. Okay, so 2 pi over 4 degrees click, where each of the handles moves to the next one. Okay, so that's some sort of a mapping class. It has order 4, but it's sort of boring. Turns out that most mapping classes are not one of these two types. So Julia alluded to this in his talk. He was saying that pseudo-Nassau maps in the mapping class groups are generic, and if you do a random walk, you will almost surely get a pseudo-Nassau. So maybe let me go back and tell where that pseudo-Nassau business comes from. So this is known as the Nielsen-Thurston classification. It says, so this was partially done by Nielsen, but people didn't notice for a very long time, and then Thurston finished it. So what it says is that if you have a mapping class, an element of the mapping class group, it falls into one of the following 3 categories. It's either finite order, or maybe let me write periodic, which means that there is a power of F that's isotopic to identity, or it's reducible, like a Dane twist, which means that there exists a collection of curves that is invariant under F. For example, a picture would be, maybe you have your surface like this, and then you have a collection of curves, maybe something like this, okay? maybe these curves just go back to themselves. It's a disjoint collection of simple closed curves. A collection of simple closed curves, disjoint collection of simple closed curves. And it does whatever it does in the complementary region. Maybe if the topology matches, maybe it even flips the complementary regions as well. Okay? So that's what called reducible, meaning that, you know, up to passing two powers, you can reduce your homeomorphism to homeomorphisms on smaller pieces so that you can understand the smaller pieces and then patch it up to understand the bigger piece. And the third one is not the first two. Okay, so these are called pseudo-Nasko. Okay, so maybe one definition that's sort of a cheating definition is that no curve is ever fixed. No curve on the surface is periodic under applications of F. Okay, which means that it doesn't matter which curve you take on the surface. You could take, oops, maybe let me not go there. You take any curve on the surface, and if you apply this F infinitely many times in forward and backwards direction, you will never be isotopic to yourself. Okay, so the formal definition is slightly more complicated. It says the following: there is a pair of transverse foliations. So I'm just going to say it really fast, so that no one asks questions. There's a pair of transverse foliations on the surface, so that this map extends, stretches in one direction and contracts in the other direction. So it sort of looks like the 2-1-1-1 matrix acting on the torus. There is one direction, an irrational direction, which is stretched, and there's a sort of orthogonal direction or transverse direction that is contracted. Okay, so locally it behaves very nicely. Locally it just behaves like, you know, a really nice matrix. But globally, if you take any curve on the surface, it just never comes back to itself. It just gets wilder and wilder. In fact, it grows exponentially. Its length grows exponentially. Okay, so as Julia mentioned, so these pseudo-anosons are actually generic. So I'm going to denote them by, or write them by PA. So these are generic. And they're actually generic in any reasonable sense of the word. So if you have a random walk with reasonable support, then almost surely you'll get a pseudo-anoson. And Ivanov proves that if you have a subgroup of mapping class group, unless that subgroup really tries to not have a pseudo-anoson, meaning that the entire subgroup fixes a curve, then you can actually combine all those reducible elements to get something pseudo-anoson. And recently we learned that it's generic in many other senses as well. Okay, so so these are really the ones that one should pay attention to while studying these subgroups of mapping class groups. And they also come with the extra bonus that if you want to understand tree manifolds by taking a surface and crossing with an interval and gluing to top to bottom, so this is called the mapping tori construction. It turns out this construction gives you a hyperbolic tree manifold if and only if F is isotopic, so you don't also map. So sort of these are like making it clear from so many different directions that they are the best type of mapping classes. Okay, so what does these things, what sort of dynamics these things have, right? So I said no curve ever comes back to itself, right? So what happens to them? So if you pick your favorite curve and apply F 1 million times, so it doesn't come back to itself, but where does it go? Right? That's a natural question to ask. And if you take two different curves and apply 1 million power of F to one of them and 1 million power of F to the other one, if they go somewhere, is it the same place, right? So to make sense of this problem, so you sort of have to come up with a new space, invent a new space that includes the set of curves as a natural subset. Okay, so it turns out that space is the space of laminations. Okay, so these are called measured laminations. and you can projectivize these, whatever that means. And this set, PML, contains the set of curves, set of simple curves as a dense subset. Okay. And what Thurston did is that this set of projective measured laminations is actually a sphere of some dimension. And if you have a pseudo-Nassau map, which acts on this in a natural way, they have north-south dynamics. So what they show is that there's this stable lamination and an unstable lamination. So you should imagine these as really complicated curves on the surface that never intersects itself, but it's all over the place. And another one which is transverse to that. And if you take any curve, your favorite simple closed curve, and if you keep applying your pseudo-Nassau, then they're going to converge to this mu plus. And it's going to be true for every other curve. There is nothing special about the curve I started with, regardless of which curve I pick. And if I apply this map again and again, it's going to look more and more like this very complicated infinite curve. Okay, so that's called north-south dynamics. Again, despite being a non-hyperbolic space, it's a sphere. It has some hyperbolic features, which comes in handy. And Ivanov shows this. Ivanov uses this and more to prove that the mapping class group satisfies the Tits alternative. Okay, so this space of measured laminations, you can think of it as the completion of set of all simple closed curves in a reasonable sense. So you can take limits of simple closed curves and get these infinite objects, and that's the space of measured laminations. But what about non-simple curves? So these measured laminations don't contain non-simple curves, but what happened to them? So if you have a non-simple curve like this, and then if you keep applying your pseudo-Nassau map to this non-simple curve, does it get longer and longer? Does it ever come back to itself? And if it doesn't come back to itself, does it have a limit? Okay. So in order to make sense of that question, you introduce geodesic currents. So that's sort of the main bulk of the survey paper, talking about geodesic currents. So geodesic currents were introduced by Bonahon to study the geometry of Teichmüller spaces and hyperbolic tree manifolds. And it turned out to be a lot more useful than that. So what's a geodesic current? So let me write down a definition, which is super scary and unpleasant, and then tell you a cute version. Okay, so geodesic current is the following. So you have a surface, and I'm assuming that I always have a hyperbolic surface so that the universal cover is just H2. Okay, so this universal cover has a boundary S1, which is this. Okay, and you can look at all the bi-infinite geodesics on S1, like these. Okay, so this is the set of all bi-infinite geodesics on S1. I'm not going to care about the parametrization. I'm not going to care about the orientation. So let me denote GS tilde as bi-infinite geodesics on universal cover of S tilde. Okay, so not caring about the orientation, not caring about the parametrization means that, well, I just have to tell you where the two endpoints are. Okay, so this GS tilde is just S1 cross S1. You just tell me where the endpoints are, but you quotient by the Z2 action so that you don't care about the orientation. Okay, so that's the space on which I'm going to define measures on. So a geodesic current is a locally finite irregular Borel measure on GS tilde, which is invariant under the fundamental group. Okay. So if you actually have a dynamics background, this is totally fine, because dynamics people like measures. Dynamics people are okay with locally finiteness, Radons and stuff. But if you're coming from geometric group theory, this makes you dizzy a little bit. So I'm going to tell you an interpretation or an example of a geodesic current, which is a lot more concrete. So I said the space was introduced as a generalization of a curve on a surface, and I should explain that in a minute. So what can you do? Let's say that you have a curve on your surface, okay? So what you can do is you can look at all the lifts of this curve in the universal cover, okay? So I'm going to use the blues as well. So it's just a collection of curves. It's a discrete subset of the universal cover, because there is pi1 as many of such curves, right? So you look at one lift, and every other lift is just obtained from that lift by the pi1 action, by the that group action, okay? And you just assign a drag measure to each of these things. And since S1 has the natural topology, the Borel topology, so if somebody gives you an open set inside of this, which is an open interval cross an interval, then you can ask how many times does the lift of that geodesic intersect that interval cross interval. Okay, so if it intersects twice, then the measure of that thing is, the measure of that set is 2. Okay, so these form some sort of a sub-basis for the topology. So once you define it for those, it comes for free for everything else. Okay, so you can think of a closed curve, and not necessarily a simple closed curve, because these lifts intersect each other, as a geodesic current. Okay, it's clear that it is pi1 invariant by construction, because if you move these sets by the action of pi1, you will just see the other copies of the lifts that is moved by pi1. Okay, and locally finiteness requires tiny bit of work, and it just comes from the discreteness of the action, discreteness of the group. But that's sort of the archetypical example. Okay, so then you can ask, like, what sort of space is the space of geodesic currents? So let's say curve S is the space of currents on the hyperbolic surface S. Okay, so one bad thing is it's infinite dimensional. Unlike the space of laminations, it's infinite dimensional. But one good thing is that it has a projectivization, which is compact. So if you projectivize, meaning that these are measures, so you declare two measures to be same if they are positive scalar multiples of each other, then this is compact. Okay, once it's compact, it's good because we can do some sort of dynamics. We have some sort of continuous transformations acting on these, and it's compact. Maybe we have some fixed points, and we can analyze these fixed points, and we can try to analyze what the behavior of other points under this action is. Okay, so that's what the second part of this paper does. So it basically understands dynamics of pseudonozzles acting on the space of projectivized currents. Okay, and how it does is using what's known as length functions. So that's sort of the main theme in the paper. Given a curve, there are many natural ways of measuring the length of that curve. For example, you can put a hyperbolic metric on the surface, and you can ask what's the length of the shortest representative of that curve, which turns out to be the length of the geodesic representative of that curve. And you can vary the hyperbolic metric and get lots of different functions. Okay, and using a length function, we prove this is probably known to experts, but we just give a a written proof of the fact that pseudo-Nosov maps act with north-south dynamics on the space of projectivized currents as well. So what this means in particular is that, well, we already knew from Thurston classification that non-simple closed curves, not simple closed curves were never fixed, but also non-simple closed curves are also never fixed. And they also converge to this stable lamination, which is an infinite object with no self-intersections. Okay, so that's about the second part. Then I'm going to say a few words about the first part of the paper, but let me stop here and ask if there are any questions. Okay. So what's the first part about? So as I said, sort of the theme of this this paper is using length functions. One of the length functions comes from Bonahon's original work on geodesic currents, known as intersection numbers. So given a surface, there's something called the geometric intersection number between two curves. Okay, so the geometric intersection number is the minimal intersection of these two curves in their homotopy classes. I think Yandi talks about this in her pre-lecture. Okay, and given two curves, and if you want to realize the geometric intersection number, you just have to put them in geodesic position, or you just need to get rid of the bigons. Okay, so this is sort of very explicit, and like you can put your hands on and tell if two things are in minimal position and if you're realizing the intersection number. And this is just a number. What it does is that it takes two curves and gives you a number. Okay, now we have this bigger space of measured laminations, and it contains a set of simple closed curves, and we have this bigger space of geodesic currents, and it contains simple curves, it contains measured laminations, and it contains non-simple curves as well. And it turns out, actually, it even contains a copy of the Teichmüller space as well. So this is this infinite dimensional giant space, which sort of encodes all the possible things you can imagine about a surface. And you can ask, well, is there an intersection number between these two things? Like, for example, if I have any two currents, not just curves, is there a well-defined intersection number that extends the intersection number between curves? Okay, so that's the question answered by Bonahon. He says in his 86 paper that there is a continuous bilinear homogeneous function, let's say I, from space of currents cross space of currents to R, well, actually, non-negatives, such that if you look at the intersection between two currents that come from actually curves on surfaces. So I showed you a way of constructing currents from curves by just lifting them to universal cover and putting the drag measure on each lift. This is going to be that intersection number. Okay, so this is I Bonahon, and this is I geometric. Okay, so there is a function that actually extends to this infinite dimensional space of currents. That's a continuous extension of the usual geometric intersection number. So it turns out that this is an incredible theorem, and then this intersection number is used in lots of things. I just want to mention one thing, which is Mark length spectrum rigidity. This is the work of Otal, Crook, and others, including Noel, which determines a metric by using the length of curves on surfaces. So there's a huge, so just for hyperbolic metrics, this has been known for a very long time. There are only finitely many curves. If you know their lengths, you can determine the metric uniquely. But if you allow more sophisticated metrics like negative curvature, variable negative curvature with singularities, etc., you can make the metrics more and more complicated. And you can ask, well, if I knew the length of certain number of curves, can I determine the metric uniquely? And lots of people worked on this. And the main tool basically in this Mark-Length spectrum rigidity problem is the space of geodesic currents. So I want to sort of advertise how cool these space of geodesic currents are before going back to what I was going to tell. Okay, so Bonahon introduces this intersection number. And one way to get a length function from this intersection number is the following. So you can take any filling curve. You can take any filling curve. Filling means that it intersects every curve on your surface in a non-trivial manner, and then you can just define, let's call this gamma, and you can just define the length of a curve as the intersection number of gamma with alpha. Okay? So that's one way of measuring lengths. And another, and a famous one, is that you can look at the lengths of curves with respect to a fixed hyperbolic metric. Okay, so length in a hyperbolic metric. And then again, Bonahon shows that you can actually see this as an intersection number with a current called the Liouville current. So it shows that the length with respect to a hyperbolic metric of any curve is actually equal to the intersection number of that curve with the corresponding Liouville current. Okay, and there are many other ways of doing this, some algebraic, some topological. And in the paper, we sort of explore these different ways of looking at lengths and counting curves with respect to a certain length. So now that I said counting, so what do I mean by that? So given a hyperbolic surface, let's say you just put your favorite metric on it, and you want to ask how many closed curves there are on that surface. Okay, how many closed curves are there? Okay, how many of them? Any guesses? Okay, so maybe let's start with a non-hyperbolic example. Let's just start with the torus. Okay, so you identify the opposite sides, and you get a torus. Okay, how many closed curves are on the torus?
SL to Z many?
Infinitely many, right? It's Z plus Z many. So the number of curves on the torus is actually, or actually in any hyperbolic or in any surface, the number of homotopy classes of curves are in one-to-one correspondence with the conjugacy classes of elements, right? So curves on S, there's a one-to-one correspondence with the conjugacy classes of elements. Okay, so in pi 1. Okay, so for the torus, the pi 1 is Z plus Z. Okay, so that means for any integer point in R2, you have a curve that corresponds to that point, right? For example, if you have 2, 3 in Z2, there's a curve. Well, maybe I'm going to do 2, 1 because 2, 3 seems such a big number. there's a curve on the torus, which winds around one direction 2 times, the other direction in 1 time. And you can do this for any pair of integers, so negative and positive. Okay, so the non-trivial conjugacy classes correspond to non-trivial paths of the torus. Okay, and if you were to count this, so what does it mean to count? There is infinitely many. So one way to count there are infinitely many is count in larger and larger balls. Okay, so if you want to look at how many curves are there in the ball of radius r. Okay, so that's actually a very old 200-year-old problem known as the Gauss circle problem, right? So you can think of the universal cover of the torus as R2, and you have the Z2 action on R2. You have the Z2 lattice inside of R2, okay? And then you're taking a big ball of radius R, and then you're asking how many lattice points are inside of this big ball of radius R. And what happens to this count as you go towards the infinity? If you make R bigger and bigger, what happens to this count? Okay, so you can probably guess by taking squares around each one of these things, you can make the estimate that there is roughly R squared many of them, right? So it's in the order of R squared, but it's also proportional to the area. So roughly pi R squared integer points in the ball of radius R around 0. Okay, so these integer points, they correspond to loops on the torus. But maybe if you look at these 2 points, they are kind of boring, right? In the following sense, maybe one of them will correspond to this loop that goes over the meridian once, but the other one is the same loop, but just that goes over twice, right? So that's sort of like the same thing. You're traversing the same path, but just you're going twice. Okay, maybe you can ask, well, what are the loops that doesn't do that? Like, how many of them are there? Okay, so in order to do that, this is the visibility problem in the forest. So if you think of these points as trees, and if you're standing at the origin, which trees can you see or can you not see? Okay, for example, all of these are blocked by this first one. Okay, so you're only interested in the ones that just goes through that path only once. And these are called primitive points, primitive integer points. Okay, and then you can ask the same question. How many primitive integer vectors are in the ball of radius R based at 0? Okay, so this immediately becomes a number theory problem. So this is about so a vector is a primitive integer vector if the denominator and the numerator are relatively prime. So the question becomes, if you have all the numbers between 0 and R, or maybe negative R to R, how many of them have relatively prime denominator and numerator? Okay, so that's a number theory problem, and number theory people know how to compute these things. Okay, so it turns out the answer is 6 over pi squared of R squared of them will be primitive. Okay, so this is the polynomial of degree 2. Okay, now that's the flat case, and as is always the case, the situation is way different when it's the hyperbolic case. So if you have a hyperbolic surface, okay, so on the torus, the number of curves, the number of 4 curves, is quadratic. And you can ask, well, how many curves are there on a genus G surface where G is bigger than or equal to 2? Okay, so one thing that you can actually get from geometric group theory is the following. So sigma G contains lots of free groups because you can look at the action of sigma G on the hyperbolic plane, and it has two sufficiently distinct elements. So that means there's lots of free groups inside of sigma G. And since the number of homotopy classes of curves is the number of conjugacy classes of elements, so that means it is at least as many as the free group, and the free group grows exponentially. Okay, so the number of curves is exponential. Okay, by just from a simple geometric group theory ping pong argument, but a lot more is known actually. So we know what the precise asymptotics is. So I think this is attributed to Huber in early 20s, that the number of curves gamma whose length is less than or equal to n is asymptotic to e to the L divided by 2L. Okay. Again, this has connections to number theory. So maybe I should mention some names, Selberg and Margulis, who has done lots of things about periodic orbits or dynamical systems, hyperbolic dynamical systems. But the number of all curves grow exponentially. Okay. And then now you can ask the same question. Well, maybe all curves is too much, and I just want to count the ones that don't self-intersect. I just want to count the ones that are simple closed curves. Okay. And how many of them as I increase this bound longer and longer. Okay. So that was Mirzakhani's thesis. So Mirzakhani, there has been some previous work, but she gave precise asymptotics and with a lot more details. How many curves, how many simple curves. So before Mirzakhani, there are three names. One of them is Reeves, which is usually overlooked in the literature. She actually proved that number of simple closed geodesics grows polynomially with the exponent 6g minus 6, which is the dimension of the Caglar space. But then, not noticing this result, Berman and series gave the upper bound 6g minus 6, and Riven gave the lower bound of 6g minus 6. Okay. But this problem turns out to be a lot harder than counting all curves. It's sort of equivalent to the following problem, counting curves of a given type, counting curves in a mapping class group orbit. And the techniques Mirzakhani uses is incredibly difficult. She talks about volumes of moduli spaces with the Weil-Peterson metric. She evaluates incredible integrals that no one should even try to integrate. It's incredibly difficult, but the results are amazing. So what Erlandsson Soto does is sort of recast these problems in the language of geodesic currents and get simpler proofs of Mirzakhani's theorems. So maybe I'm going to finish with a fun fact that comes out of the incredible papers of Mirzakhani in her thesis. So for example, if you have a genus 2 surface, okay, you have two types of curves. So a curve could be a non-separating curve, which means that when you cut it open, the resulting surface is still connected, or it could be a separating curve. Okay. And then she asks, well, randomly pick any two curves or any curve whose length is less than or equal to L. What is the probability that it's going to be separating, or what is the probability that it's going to be non-separating? And she proves that it is 48 times more likely, like exactly 48 times more likely to be non-separating. Okay, and how does she prove this? She computes of volumes of moduli spaces with respect to the Weil-Peterson matrix, and she has these amazing recursive formulas. And it's sort of an incredible theorem that not only she gets the asymptotics, but she tells what the exact numbers in front of them are. And she also uses geodesic currents along the way. So I guess I'm here to hype up geodesic currents. Okay, I'm done.
Thank you so much, Chala, for your talk. We definitely have time for a question or two. So if you have a question, maybe just say it out loud or try to type it into the chat. Just making sure there aren't hands. Okay, well, I have a follow-up comment in case someone's just typing. I love hearing people who think about mapping class groups define geodesic currents, because it's never the way my brain thinks about it, but it's always such a good explanation. So thank you.
Yeah, maybe I want to give a few comments about the papers. It's a survey paper, so it doesn't have too many proofs. It has lots of statements. And like, if you really, really want to learn the details, say you want to learn more about laminations, you want to learn more about geodesic currents, there is also a lecture notes by Chris Leininger and Javier Aramayona. This is about currents. I think it's easier than Bonahome's original paper, because Bonahome's original paper is in French. This is in English. Also, there's a book by Erlandson and Soto. It's a 200-page book, which is pretty much self-contained. It talks about geodesic currents, it talks about train tracks, and it proves Mirzakhani's theorems, even the original ones from the point of view of geodesic currents, which is also another great resource if you want to learn more about these things other than the general overview.
Oh, well,
And
thank you for
like
good resources.
Yeah.
Sorry, what's the title of the book?
It's Mirzakhani's curve counting.
Oh, is that the one that just came out last year?
Yeah, it's just a new one. Yeah.
Yeah. Okay. If there are no other questions, let's thank Chala again. Thank you.
Thank you.
We have a little break built in because you've been listening